Triple integrals and center of mass. Here's a very simple formula. X bar is just a triple integral over the solid region rho x dv. And rho dv is an element of mass. And if we integrate rho dv, that will give us the mass. The mass appears in the denominator of all three of these. The y coordinate, we just change x to y. Z coordinate, the center of mass, we just change y to z. A fairly simple symmetric formula. Consider this familiar solid region, this Cartesian product, 0 to 1, 0 to 1, 0 to 1, a unit cube. And suppose we have density 2x kilograms per meters cubed. This is a mass per unit volume density, which we're used to in the physical sciences because we have a solid region. Let's find the center of mass. We're going to start with x actually because there's an x here. We can predict what y and z are. That's pretty easy, but we'll start with x. Well, first of all, we're going to find the mass. Triple integral rho dv, that's just this integral right here. Rho is 2x, and oh, got that extra x in there. 2x dz dy dx, and we have integral 0 to 1, integral 0 to 1, 2xz from 0 to 1, dy dx. Plug that in, we get a 1 minus 0. And so this is going to give us integral 0 to 1, integral 0 to 1, 2x dy dx. We've done this integral before, but we'll do it for completeness. 2xy from 0 to 1 dx. And plug in 1, we get integral 0 to 1 2x dx, which gives us x squared from 0 to 1, which is 1 kilogram. We have a mass of 1 kilogram. On the surface of the Earth, it weighs about 2.2 pounds. So this is meters. That's a pretty big object, 1 meter by 1 meter by 1 meter, and it has a mass of 1 kilogram. It's not very dense. Second of all, this mass, you can use that. Let's just make a record of that. M equals 1 kilogram, and that will appear in the denominator of all these calculations. And now we just need to integrate rho x dv, rho y dv, and then rho z dv, and that will give us the center of mass. And this is 0 to 1, 0 to 1, 0 to 1. Rho is 2x, x, dz, dy, dx. Incidentally, when we have constant limits of integration with the cube, you can switch the order, just have to switch the limits. This was 0, 1, 0 to 2, 0 to 3, for instance. Z would go from 0 to 3, and then y 0 to 2, x 0 to 1. You can switch these. As long as you switch the limits, you can switch this order. It's pretty easy with a cube. So now in any event, we have 2x squared dz, integral 0 to 1, integral 0 to 1, 2x squared z from 0 to 1, dy dx. Okay. And plug 1 in, we just get 2x squared. And so we get integral 0 to 1, integral 0 to 1, 2x squared dy dx. And that gives us integral 0 to 1, 2x squared y from 0 to 1. And that's just going, these are pretty boring integrals, but that's okay. 2x squared dx. Now that's going to give us 2x cubed over 3 from 0 to 1, which gives us 2/3. So x bar is this integral over this integral, which ends up being 2/3 divided by 1, which is 2/3. And the unit on that would be meters. If we draw our little picture here of our unit cube, there's x, there's y, there's z. Okay, the center of mass is right out here, 2/3 of the way from 0 to 1. It's skewed a little bit more toward here because the density varies with position. If this were uniform density, if this were like a wood block, it would be at 1/2, be right in the middle. But this becomes more dense as we move out on the x-axis, so it's skewed this way a little bit. It's beyond 1/2. It's actually at 2/3. Now, it turns out the density doesn't vary with y or z. Okay, so if you move in the y-axis, it's uniform. If you move in the z-axis, it's uniform. You may guess what the density is, and let's calculate y just to confirm your suspicion. Okay, so we're going to calculate this integral right here and then divide by the mass, which is 1 kilogram. And the units on this, by the way, you can calculate dimensionally. Kilogram per cubic meter gives you a kilogram, and then this is meters, so the units on the top would be kilogram meters. Divide by kilogram just gives you meters if you're interested in the dimensional analysis aspect of this. So we're going to integrate 0 to 1, 0 to 1, 0 to 1. Rho is equal to 2xy dz dy dx. Now we get integral 0 to 1, 0 to 1, 2xy z 0 to 1 dy dx. Integral 0 to 1, integral 0 to 1, 2xy dy dx. Now we have to integrate the y integral. Y squared over 2, the 2's cancel, and this will give us integral 0 to 1 xy squared from 0 to 1 dx. Again, we get y squared over 2, so it just gives you xy squared. Plug the 1 in, and we get integral 0 to 1 x dx, which gives us x squared over 2 from 0 to 1, which is 1/2. Okay. Okay, my suspicion was that the center of mass on the y-axis was 1/2, right in the center, because the density does not vary with y. So y bar is equal to 1/2 meters, and you can guess this is probably the same as z bar. You can go ahead and do the integration. That's exactly what you will get. So, okay, that's triple integrals in center of mass. The formula never changes. The Only different part is if this is an irregular solid, the integrations can get quite complicated, but that's just setting up a triple integral. It has nothing to do with center of mass. We'll be back with a third problem. We're going to find the volume underneath a the volume underneath the plane, which gives us a tetrahedron. The integration is a little more tricky, but I'll show you a plane problem, and then you'll have one similar in your packet. So.